Hello, everybody. Welcome to Happy Maths Hour with myself, Caroline Ainslie, and the amazing, wonderful Toni Beardon, who poo-poos me every time I say that.
Yes, poo-poo.
And today we're going to talk about, well, topology, but it's an introduction to topology. And today I am going to be asking lots of questions because Toni's been through this with me, and I've got my hat on of, oh my goodness, this is very, very fascinating and interesting, but oh my goodness, there's a lot of brain cells used up with this. So everybody switch on your brains. And as the wonderful Paul Erdos used to say, my brain is open. So open your brains. He didn't say my mind is open, he said my brain is open. He was Hungarian.
Well, this is easy stuff. It is very easy. And it's the sort of thing that teenagers can do in school. And it's a pity if they miss out on this, because it's giving a perspective of what maths is about, what it involves, and how and why it's useful, and what mathematicians do in solving problems that affect us all, that affect society. So
it's interesting. It's fascinating. So when teenagers say, "Why bother?" it's because it's fascinating. And here's a perfect example.
Well, they're not ready to do it yet themselves, and the problem is that there's a lot. The problem is that there's a lot to learn, and you speed up as you get older. You don't learn. You learn fastest when you're very young, when you're about a year old. And then you don't learn as fast in school, surprisingly, but you actually, it depends on, well, maybe I'm wrong about that. You learn a lot of different things in school, and if it's a very good school, you learn the most important thing of all is how to learn,
and how to become a lifelong learner, how to be excited about learning,
and to understand everything you do, because rote learning is useless, and a lot of school is unfortunately, because that's what school exams are about. Anyway, let's go on.
Right, so let's do it. Oh, here's my itchy bugs again.
Yes, and here is an Escher wood engraving of a Mobius strip, and you see that it's quite hard to know where the bugs are. Which face are they on? Are they on the outside or the inside? Are they on the top or the bottom? Well, we're going to do something more on the Mobius strip, and we're going to lead up into that, from that into topology. Now, here's my little ladybird that we looked at last week, and the ladybird is on a railway track, and the ladybird can go round and round that track, but only on that side, and so on that surface, and not on the side that's been shaded green, which I call green grass.
So the ladybird's going on the internal loop, like loop the loop, and if you go and then the other one is that really scary ride. Go on, the one on the outside of the loop.
Here we've got no twists, and so effectively, this ladybird is on the inside of a cylinder. Now here, this is a Mobius strip, and in order to make the Mobius strip, we change the points just where the ladybird is positioned now by twisting the strip through 180 degrees and joining the two ends. What we made was a Mobius strip, and now that's like changing the points on the railway track, and the ladybird can go from the railway that has got no green onto the green railway, all the way around that and back onto the other rail. So the ladybird can go over the entire inside and outside surface and keep going on round, over, across and along both surfaces. So that's a Mobius strip. Now, to recap on that, there's a cylinder, and by joining, if you just take a flat sheet and you just join it, you make a cylinder, and you just join one edge. But if before you join those edges, you do a twist, you make the Mobius strip. So that's what we just showed you with the ladybird. But you could join both edges Now imagine joining the top of the cylinder that you see to the bottom of the cylinder, and you make what we call a torus, but it's also known as a donut in common English. Okay. And on the right, you see something else, which is the natural thing to do if you think about what we did with the Mobius strip. But instead of joining the top and bottom of the cylinder, we did a twist before we joined them. We get something like that KLEIN bottle. So in a sense, the KLEIN bottle is rather like the torus insofar as the two edges of the strip are joined. But it's more like the Mobius strip in that you twisted one edge, you turned one edge by 180 degrees. So, but they're all, to point out that they're all two-dimensional surfaces. We have to come out into 3 dimensions to show them, or at least you've got to imagine the 3 dimensions, but we're just imagining the surface, not what is inside the surface. Now, what's about connectedness? So mathematics has no thickness, just like a point has no dimensions at all, and a line has no dimensions. It's long, but it's not, has no thickness at all. So when we compare the surface of a cylinder torus, what we do is we think about what happens outside those surfaces, and any 2 points not on the cylinder can be connected by a curve. One of the points might be inside the middle of the cylinder as you see it, and the other point might be outside. But by doing a long curvy path, you can go from one point to the other point continuously. So the whole area that's not part of the cylinder, not part of the surface, is what we call connected. You can join any 2 points with a line. Is it the same for torus? Now here you have a problem, because the torus, the surface of the torus, has, imagine blowing air into an inflatable tube. It's got an inside and an outside. And so you can't connect a point inside the torus, the surface, to a point outside without going through the surface. So it's not connected. The torus is a surface that's not connected. These are
so basically there are points inside the torus that cannot be connected to points outside the torus without going through the surface.
You've got it, Caroline.
Whereas with the cylinder, every point inside the cylinder can reach a point outside the cylinder just by going out the top or the bottom.
Yes. And
okay.
Just having a line that joins them. Yes.
Right. Okay.
Now, it's not particularly important to remember this or to learn it just now. It's just one of the ideas about topology that we're just throwing into the mix to give you a glimpse of topology. And this is about, yeah.
I just wonder if the difficulty, I mean, because the reason why I do what I do is because one of my big problems is memory. And so to me, I'm like, what was that word? How did we describe it again? And it's not so important to know, oh, yeah, it was connected or not connected. That's kind of, I guess, important for an exam or if you get further advanced. But just having the concept, okay, the torus is different because it cannot, a point inside cannot connect to a point outside without going through the surface. That is a really, really simple concept to grasp.
They're all simple concepts, and what I'm trying to do really is just to sort of get an overview so that we can understand that there's quite a few things that can be different between one surface and another, and there are properties of the surfaces that might be relevant, and a bit later we'll see how they're relevant and useful.
Oh, Toni, I've come up with a real life way of really visualizing it. If you had a needle and a thread and you were going to connect one end to the other, you can take the needle out of the cylinder. But if you had a needle and a thread inside or outside the torus, the only way to get in is by popping the torus.
Yes, puncturing it, yes. Yeah. So how do these surfaces sit in space? I mean, how do they relate to the space around them? So there are two very different types of loop on the torus, the red one and the black one there. You see, the black one goes around the ring, through the middle of the ring and back to join itself. And the red one is on the surface of the ring but doesn't go through the hole. Now, they can't be shrunk to a point and stay on the surface. Neither of them can stay on the surface and be shrunk to a point. So imagine them getting smaller.
By definition, a torus will always have space inside the tunnel, and so there's two places that will always have. I'm assuming, I'm kind of going there with this. You've got the actual, let's call it a tunnel. I'm going to call it a tunnel. So that you've got that's never going to become zero with a torus. And then the hole, the donut hole itself, is never going to become zero. So it's never going to merge into a dot. Because otherwise it wouldn't be a torus. It would be a point. So by definition, a torus doesn't go down to being a dot.
Exactly. So so there's a torus there. I mean, there's a surface there that's like a tube, which is joined to itself. And as Caroline says, because it doesn't shrink to zero and the hole doesn't shrink to zero, if you shrink the loops, there's going to be, you can't make them any smaller. You certainly can't shrink them to a point.
Yeah, so basically it's not, if it's a point, it's not a torus. So as long as it's still a torus, it's by definition, loop 2 cannot go to zero, or it wouldn't still be a torus, and loop 1 couldn't go to zero because it wouldn't be a torus anymore.
Exactly.
Whereas, what about a sphere? Can a sphere be reduced to a point?
Well, in both cases, the answer is that this is the extreme case.
Yeah.
But we're not going to that extreme.
Let's not. That's a good idea. Let's just not.
As long as we've got this ball or sphere, the loops, even if they start off being the biggest loop possible on the surface, which we call a great circle, they can still be shrunk to a point. Right. All the loops on the sphere can be shrunk to a point. So there's a difference, another difference.
Okay, so it's a point on the sphere. So you still got a sphere, but the loop can be shrunk to a point. Okay, exactly. Whereas, so by definition, you've got a sphere, but the loop can be a point, whereas, and the sphere still be a sphere. Whereas the torus can't still be a torus, and those loops go down to a point because it wouldn't be a torus anymore.
Well, you'd have to change the torus. You've got to imagine the torus as you see it, and the only thing you change is the loop.
But it wouldn't be a torus anymore if it was a point. It just wouldn't be a torus. Whereas you can have a loop that is a point on a sphere. You can't have one of those loops on what is still a torus as being a point.
Well, I think you're changing the torus in your head rather than changing the loop.
No, that's what I'm saying is that you can't. But as long as it is a torus,
the idea of the torus, you can't. There's exactly the small for any given torus.
Yeah.
There's the smallest loop that you can make of type 1, and there's the smallest loop you can make of type 2.
Yeah, I can see that. Whereas you would, if that loop could go down to just a point and the sphere would still be a sphere. It'd just be a point on a sphere. Yes. Yeah, I can see that. When we were talking about it earlier, I wasn't getting that clear about it, but I can see it now. I like it. I'm happy.
So topology is the study of differences like that. Both of the surfaces in their own right the way that we study the way that they are embedded in the space around them. And so we saw connectedness. We've now seen this idea about shrinking loops to a point. And so topology actually looks at surfaces with different numbers of holes in them.
I'd like to just point something out. I've just had a realization, and that is that I didn't get that explanation the first time you said it, and you have said this before, and this is the first time, by hearing it again and again and asking questions and going over it again and maybe asking a few different questions, now this is the first time I've really started to get it. So my point being that if you're watching this and you find, oh, I'm not getting it, it just means it's the first time you've heard it, perhaps, or you haven't heard it enough times, or you haven't seen it from different perspectives. So that's just an interesting insight. If you think, oh my goodness, I'm not understanding this, it's just that you haven't gone over it enough times in enough different ways.
But it is a bit strange. It is a bit strange.
Which is why you have to hear it a few times.
Well, yes, I think you've got to think about it. You've got to have time to think about it. Now, what we're looking at here is, when are things topologically equivalent and when are they different? And we've been looking at the torus and the sphere, and we've seen some differences between them about shrinking the loops and about connectedness. But look at these things on the left.
I'm adding my coffee cup to the mix.
Yes. So the coffee cup, or teacup as it's labeled on the picture, if you imagine it being made of clay that was still soft, you could mold the clay without changing anything about the number of holes. You don't break your clay anywhere. It's broken through the handle, but you don't break it again. And if it was soft clay or plasticine, you could just mold it and mold it and mold it. You can make the hole bigger, and you would get the donut or torus shape.
So you could do that as an activity. You could do that literally. You could make a penguin with a hole, or a scrunchie, any kind of thing with a hole, or you could form a teacup or a teapot even, and then, as long as you
be careful about the teapot. That's got
oh my goodness, it's got another hole.
It's got the handle of the spout.
Ooh, shush. Oh my goodness, so it does. You've got to really think about these things, haven't you? It's not the
so
same.
If you look at this crunchy thing
hole
in my hair,
I've got
the picture there's Caroline's. Okay,
I've taken mine
you
out.
Imagine stretching it and smoothing it and blowing it up from the inside. You can actually imagine it's topologically equivalent to a torus. It's got one hole in it.
And it doesn't have to be, it doesn't have to be circular. It could be rectangular.
Yes.
I'm correct in saying that, as long as it's just got one hole in the middle. And a teapot won't do it, because a teapot's got two holes. Silly me.
And we often have floaty ducks for little children as swimming aids. So they put it round them, and then they can lean on the duck and kick with their feet and be safe in deep water, or relatively safe. Oh, why not have a flamingo or a penguin? I think they're rather charming. But you could squash in their little heads and stretch it, and if it was all sort of elastic, you could make it into just a smooth ring. So all of those things are topologically equivalent. This is very strange, because in the geometry we study, we don't change distances and angles. We just work with them and think about them. But in topology, we don't have any distances and angles, or at least they're not important. So what's the top?
This is not geometry. It's like
geometry.
Not geometry. This is very conceptual. And it makes me brain ache a little bit, but it's very fascinating.
But you see, you're not going to have to learn it at school or be examined on it. But that's the joy of it, because basically it's much, much, much more conceptually deep and useful than what you do learn at school. And you can understand it.
You said
right?
useful. I think you're going to tell us just how useful it is in a little bit.
We are indeed.
Who would have thought that topology, this about how many holes there are in my teacup, and that isn't a hole, because topologically it's just an inside surface, but there's not actually a hole. It's actually useful. There. No puncture.
Otherwise,
no hole in the bottom. Otherwise, my coffee would be coming out the bottom,
yeah.
or out the side. I'd be drinking and I'd be getting coffee pouring down my front.
Yeah.
Okay.
Yeah.
Keep going.
So the thing is that you do have to learn a lot more maths, because the maths you learn in school, you haven't reached this point of learning enough to really understand what you do with the topology in the deepest way. But the computers do a lot of it anyway. But when you have done a university course in mathematics or engineering or one of the sciences or computing, and then you've done more study and you keep working, you can make a lot of use of topology. Okay.
Now, do not reveal this. Do not reveal this yet, Toni.
Oh, yes. It's a question. What's the topological difference between a sweater and a pair of trousers? In other words, how many holes are there in them? I don't mean holes where they've got worn. I mean holes where you put your legs and your arms and your head and your body.
That would depend who was wearing it, wouldn't it? Like when I was a kid, I always had holes in my elbows. So I actually got this wrong. I'll just put my hand up and say I actually got this wrong. And it's not about getting it right or wrong. The wonderful thing is that when it's revealed, it's a big aha if you, like me, get it wrong the first time around. Oh, hold on, we've got a comment. Let me see if some. Oh, Avuyo Melane. I'm assuming from AIMSEC. This is a very interesting topic, Toni.
Right. Now, it's what you see in your mind's eye. Okay, what you visualize. How many holes are there so you can put a sweater on? You can put your hands through the sleeves, and you can pull it down and get it on you when you get dressed. How many holes does a sweater have? And how many holes does a pair of trousers have? Well, here you go.
Oh no, I was going to tell my answer first. I said
Caroline.
3. I know, but no, I wasn't going to give you the correct answer. I was going to tell you my original answer. I forgot all about having to get the body into the sweater. I only said 3 for the sweater and 3 for the. I remembered I had 2 feet and a waist, but I didn't remember that I had a waist on the sweater. So I actually said 3 for both. You've got to think about it.
So neither of them is equivalent to a torus. Here you've got.
This is Toni's artwork, by the way, folks. If you're very lucky, you'll get a signed copy. You can frame it on your wall.
So your sweater's got 4 holes and your trousers have got 3. Okay. So why topology? It's something that you may hear about a little bit. And you wonder, well, how could it be useful? Because what you've learned, I'm sure, in school, maybe still in school or maybe a while ago, but it was about geometry and a particular sort of geometry, not about topology. Now, physical situations are described by sets of parameters. What does that mean? Think about it, though. A physical situation is something in the world around you, okay? And the parameters are just things that change, can be measured and changed.
So just pause there for a second. The parameters are things that can change.
Measured and changed.
Measured and changed. So I'm just going to rephrase that, and not rephrase it. I'm just going to reiterate it. Parameters, because that came up with the communication course, didn't it? Parameters are things that can be measured and changed. Okay, go on. So
space-time, a point that moves in 3-dimensional space.
Okay, so we've got up, down, left, right, and forwards and backwards. So that's 3 dimensions. So that's 3 parameters because they can
And
be measured
time.
and changed. And
So if it's
time.
moving, where is it at any given time? So that's 4 parameters, and that's 4-dimensional space.
But this is different to the 4 dimensions that we talk about in geometry. Am I right or wrong?
Not
in saying
really.
that?
No, not really. It is a sort of geometry. Now, Einstein really made us all think about this, because when he introduced his theory about space-time and relativity, he was moving into 4 dimensions, and
because of adding time. So we have the 3 dimensions that we're well familiar with in our world that we operate in: up, down, forwards, backwards, left, right. Einstein added time as the 4th dimension.
But that's because he wanted to analyze what happened as points move, and he was thinking about cosmology and the light traveling across the universe to us. So we were looking at distant galaxies and distant stars.
Okay, and of course, if something's moving, it takes time for it to move. No matter how fast it is, it takes time for it to move, hence adding the time to the equation. And that can be measured. Time can be measured, just like distance, up, down, left, right, forwards, backwards can be measured, so can time.
Yes, and when did the light leave that star that we're seeing now? So you have to know how fast it's traveled. You're involved with time, space and time.
Okay, so you can find out where it is in space. That's your X, Y, Z, your up, down, left, right. So its location, you can pinpoint its location in space, and you can measure the time that it takes for the light to get here, which helps us determine
I can't
its
do
location.
that, but I can imagine it. Okay.
I was going to say, I can imagine it from a very, very simple conceptual standpoint. Don't even go to where right now, for me, in my current state, I'm always learning, of course, but it's just purely very conceptual, very simple in my head, but at least I can get a grip of it. Well, I can imagine it, just imagine it. A time continuum.
No, but this is science fact, not science fiction.
But they play with Einstein's ideas.
Yes.
In Star Trek.
So now let's think about something else that's really important to us. That's climate change and weather. Okay, people talk about weather all the time, don't they? They obviously think it's very important. And climate change is, well, it's a problem in the world. So how do we work with climate change and weather forecasts? We think about points on the Earth's surface that can be described by 3 spatial dimensions. Position.
Okay, so we've got our 3. We've got our forwards, backwards, up, down, left and right. We've got that.
And then together with that, we've got time, air pressure, temperature and humidity. Those 4 parameters, things that change, also determine the weather.
So I can see why we're calling it parameters, because they're variable and they can be measured. Okay.
And there are 7 parameters.
But what I'm not saying, I don't get is you say that's 7-dimensional space. I'm not that my mind is not leaping there.
Well, the space is what mathematicians call it. It's because you've got 7 things to study and they're changing, you need to be thinking of that change, and the way mathematicians do it is by thinking of them as a point in space.
Oh wow, well that sounds complicated.
But it's a new sort of space. It's a topological space.
Whoa, stop. So this isn't 7 dimensions as in what I'm used to doing my best to visualize. Well, I can visualize some things for 4 dimensions in geometry.
Caroline. Open mind.
Open my brain. My brain is open.
And we're only getting a glimpse of topology.
Yeah.
Okay.
So when you've got more than 3, well, there's basically a 7-dimensional space topologically. So we use this subject called topology to help predict the weather.
Yes, indeed we do. Okay, so topology involves the study of continuously changing parameters that define the points of a surface or of a higher dimensional object. And now here it is, this is the important thing, that may provide a mathematical model for a physical situation. So what we're saying is for weather and climate change, we've got a 7-dimensional model. For space-time, travel in space, we've got a 4-dimensional, a 4-dimensional model.
And it's the mathematical model, because we hear about that. We've heard about it a lot in the last year, of the mathematicians predicting what's going to happen with COVID, how the vaccinations are going to affect COVID. All of this is through mathematicians creating models.
Yes, and we're going to talk more about models. Now, when we're talking about the topology, there are global topological properties that determine the overall shape and the relationships in the parameter space. And there are local properties that happen in a small part of the space. Now think about us on the Earth. Now human beings changed their minds as society changed its mind about whether the Earth was flat or whether it was spherical. Now I think most people are agreed that it's spherical, okay?
Flat earthers, listen to this carefully, okay?
Now, if somebody designs a housing estate with houses and roads and the like, okay, they draw diagrams and they pretend, even though they know it's not quite right, that the surface that they're building this housing estate on is flat. Well, it might have a hill, but...
Well, they actually do make it flat because they level it with concrete. But so actually what they're doing is they're compensating for the curvature of the Earth with concrete. It's just the curvature is minuscule.
Locally, but not across.
Locally.
Yeah, but the point is the change is so small from one side of the building estate to the other, across this mile or two that it might be. It's such a small change.
You see structural engineers along the road with their little sights. You have them on either side of the road, and when they're doing measuring for buildings, and they're using their laser sighting or whatever they're using, they're doing their sighting. You've got one, like it might be 100 meters away from the other, and they want them completely horizontal. So yes, they are pretending that the Earth is completely horizontal. Yes, exactly what you're talking about.
No, I don't think this is quite the point, Caroline. They do leveling locally, but the point really is that we all pretend that where we are, and it is such an almost imperceptible difference. You've got to go not just a mile or two, but you've got to go 20, 50 miles before.
That's the point, that they're not leveling. That I was kind of being a bit facetious there. That they're not leveling. They are assuming that what they're doing is parallel with the ground.
So what we've got,
they're relying on that actually.
So what we've got on the surface of the Earth is little hills and bumps, and they hardly make any difference in terms of the whole big Earth.
Right.
Now, but supposing so that's a local property. And I mean, whatever Caroline says, we are living as if, and forgetting altogether, we're living as if we were on a flat surface, but we're not on a flat surface, we're on a curved surface, on a sphere. Now, if we then head on an aeroplane to New York and we keep going in a straight line, we'll head off into outer space because we have to go round the Earth because it's curved. So what we're trying to fix our minds on now is the difference in topology between local properties that happen in a tiny little area around where we live or where we're looking, and global properties that relate to the whole of space. Now, space travelers...
I'm going to stop you there for a moment, Toni. We've got a very, very valid question here, which is very relevant to teachers in that perhaps have never listened to a talk like this. And the question I'm getting is, this sounds very complicated. For which level does it apply? So I don't think Vuyo was here when you made that original introduction. Would you just repeat again why we're talking about something that sounds complicated, but we're doing it from a simplified level? Why are we introducing this to teachers that teach primary, secondary, FE?
Well, we're talking about mathematics, and it's one of the subjects that children in school spend the most time on. It's on the whole, in most countries, school children spend a lot of time on mathematics. And the question is often asked, why are we doing this? What's it for? What's the use of it? And the truth of the matter is that what you teach in school is so elementary and so simple that actually they're not going to be using it as such very much. So you might say, why teach it? Why learn it? And the answer is because some of those children are going to use it and need it. And there are ways, although I'm perhaps underplaying them, where they will need. I mean, a nurse needs to give the right dose to a patient. So, or you need to give the right change. You need to keep your accounts and know how much money you're spending. So there's some simple arithmetic involved. If you're making something, you'll think about how much do I have to buy of paint to paint this wall, or whatever you're doing. So there's some simple calculations, but they are relatively minor. And when it comes to earning a living, you've got to learn a lot more than you do it learn in school in order to actually be able to apply the mathematics usefully. So we're not talking about school mathematics, but what was said at the beginning, and I'm going to say it again, it's really important. It's really important to understand what the mathematics you learn in school leads to and why it's important. And what we're trying to explain now, it's not for teachers, it's just for anybody who's interested. Well, it can be for teachers, but everybody else too. What we're trying to what Caroline and I are talking about is what's topology? It's just a glimpse of topology. Where is it useful? How is it used? And what's it all about? Just a little glimpse. And the school, you don't teach topology in school at all. It's taught in university, and it's one of the most useful subjects, but you have to learn a lot to get there along the road. So let's carry on.
It's something you can do as an enrichment activity to generate interest in mathematics and say, this is mathematics. And what we're going to finish off with, Toni's going to do, and we're going to do others as well, it's things they can do with paper, scissors and tape that can generate excitement about mathematics, even if they're a bit jaded about doing the arithmetic side of it and algebra and whatnot.
The reason that, maths is a very powerful subject, and what we're teaching at school is very elementary maths, and there's a lot more to learn, and that's why it's so important to know how to learn, to be interested in learning, and then to learn more and more. So, and even if it's just so that you understand a little bit more about the world around you and you're not so ignorant. So let's move on a bit. We want to know why it's useful. So it's useful because applying maths to solve real life problems and to address issues that affect society, mathematicians set up mathematical models. And the models are described by data on a computer and equations and programs, computer programs, that model changes in the real world, in the physical situation. And studying a mathematical model involves geometry. We know a bit about geometry, we learn a bit at school, and topology, which we're talking about today, which is something you don't learn about in school, you learn about in university. So what's the difference between geometry and topology? Geometry features a system that involves measurement of distances and angles. We teach that in school. Topology is different. The features of this system don't involve distance and don't involve angles, but it's still about points in space.
Now, because you were talking about the variable parameters, which are variable and can be measured, so that's where we use topology. So these are things like actuaries, the people that work out the risk of an insurance company, the people that work out what the population might be in a few years' time, so they can work out how much food we need, what transport's needed, how many schools are needed, how many teachers will be needed, all of those sorts of things. These all, are they using topology? Are they using group theory to make all these predictions?
Anything that's probabilistic, and a lot of life is, you know, certainty is rare.
Yes.
Okay.
I was thinking earlier that you were talking about the probability of me being eaten by a shark, and I thought, well, it's 0. And then I thought, well, actually, it's not, because if I go out on a boat somewhere and someone throws me off the edge, or I happen to fall off the edge,
you're swimming in the
side,
sea.
No, you can avoid that. You can not swim in the sea. So I can guarantee not being eaten by a shark if I don't swim in the sea. But if I go on a boat and I happen to fall off, then actually it's not 0, because there might be a situation where that comes. But what's messing with my head is that I'm going from my coffee cup to working out the weather, and it's the same. The business of having just one hole in my coffee cup is the same.
What you've got to fix your mind
as working out the weather.
What you've got to fix your mind out. Let's keep it simple. Let's just think of this space which involves not just 2 coordinates or 3 coordinates, but maybe 7 coordinates, as we were talking about the weather. And these are points in a different sort of space that we don't study in school. This is a topological space, and this is what mathematicians work with. And some of the examples that Caroline mentioned were a bit simpler. The actuarial probability thing, well, yes, once you get in probability, and we're going to come, if we have time, we're going to come to discuss where probability is important. Yes, that will involve topology. So geometries involve limiting processes, things getting very small or very big, okay? And analysis, that's another subject in mathematics. Now, the geometries may be Euclidean, which we teach in school, or hyperbolic, or spherical, or other types of geometry. So the geometry that we teach in school is a very limited geometry. And when Einstein introduced his space-time, he told us all that we need a different sort of geometry, which is hyperbolic geometry. And that is just as useful as Euclidean geometry, except that we need to, we don't know about it when we're in school because it's not on many school syllabuses. But it's useful.
It needs to be introduced a little bit at a time as well. I mean, it really is, you've got to have a certain understanding before you can make the leap to hyperbolic.
What you've got in your school maths is the ingredients, and you can learn about hyperbolic geometry very quickly once you know about Euclidean geometry, because there are similarities and differences. Now,
you build on Euclidean to get to hyperbolic, but
you do it by comparison and contrast.
Okay.
So what you've got is the angles of a triangle in hyperbolic geometry don't add up to 180 degrees.
Right,
okay. They add up to less than 180. And when you go to the spherical geometry, we know more about that because that's a geometry of the surface of a sphere, and we live on the surface of a sphere. So the spherical geometry is like hyperbolic geometry. It's like Euclidean geometry in some ways, and in many ways it's very different. And one of the things that it's different, in respects in which it's different, is the angles of a triangle on a sphere add up to more than 180. And I'm going to stop there because
we've got a whole nother video on that one. So
yes, yeah. and those 3 Escher pictures that depict angels and devils, so you can see the shapes. They're all the same size, by the way, exactly. In the middle one, in the hyperbolic geometry, but distance is defined differently. Isn't that strange? Okay. Now then, probability space. Now, when we work with probability, and we're involved every time we turn on a television, we're being given these probabilistic models, these mathematical models. We're being told about what the mathematics is, what the data is telling us. Okay, that's a mathematical model of the spread of COVID. And where we study, where we use mathematical models, we are thinking about space, and it's a different sort of space to what you think about if you're just thinking about X, Y, and Z coordinates or 3-dimensional space. It's a different sort of space because it's got more dimensions very often, usually. It's got more dimensions. And the probability space is just the way the mathematicians talk about it, is a set of all possibilities. So we do teach that in school. We do teach about the sample space or the probability space when we teach probability. And it's, what is it? It's the set of all possibilities. And you can't begin to think about probability unless you understand what the possibilities are and how many of them are. And you can list them and you can say what they are. So look at these squares here that have been made with strips of paper, different colored strips of paper. And at each corner of the square, the strip either folds over itself or under itself. And we label the where we've got with the sort of orange one, we label it OU, OU. So what it's going around in the direction of the arrow, which is clockwise, and the first fold is over. So let me show you this one. Okay. I'm going to, I've got to get this in position so that I know what I'm doing, because just at the moment I don't. I'm fumbling with it. Right. Okay. That looks like. There we go. I've got it in the right position, finally. So that's over, because what you see down here is on top.
Move away from the window, Toni.
There we go.
Yeah.
Over. Now this fold,
hold on, I'm going to make you big. I'm going to make you... remove that and make you... How do I make you big? Well, at least you're half big now.
Okay, this one is under, right? This one here is over, and hold it together at the top now, right? Right, and this one is over, as you see it, okay? So you see it's like the one in front of, on the screen. So one I'm holding up is like the one on the screen. And this is like the Mobius band, isn't it? Well, this isn't a Mobius strip, actually, or Mobius band, but it's the same idea, and we're linking into the Mobius band now. Now, what this little exercise is, which we could do in school, And it would help us because we do need in order to pass the school exams, we need to be able to, for any probabilistic study, to make a list of all the possibilities. So this task, this challenge is, how many different possibilities are there if we make a square like this, folding the strip over itself at the corners and coming back to where we start? How many possibilities are there? And when we've made it, how many twists are there? Now look at this. How many twists are there in this strip? Can you see? I'm going to now reveal.
It's just a cylinder.
It's not a Mobius strip. I promise you one of the others is a Mobius strip, but this is just a cylinder. So how many possibilities and how many twists? This one's got no twists. Okay, so let's take this blue one, and we'll try and do this blue one for you. Okay, this is the blue one. So the first one goes. Oh, you want to see it so that it's under. It's just a matter of the way I'm holding it up for you. Okay.
So we've got the red on top for this one. The first one is under.
There you
red
are.
On top.
So can you see it now? So this is as you see it in the picture. It was Caroline says the red on. Oh yes, Caroline's mentioned the edge. It's quite helpful to think about what's happening to the edge here. Now then, the next one here. Oops. Here. This first one is an under, and
Vuyo said there's 4 possibilities and 4 twists. Which one has 4 twists, Vuyo?
Ah, well,
4 twists.
We'll find this out. Okay, so let's finish this one off and hold it, right? So
let's just compare it with the picture. So that is the blue one in the picture. So it's under, over. Let's just move that out. Whoops, feature Toni again.
And then this one, has this got any twists in it? Looks as if it might have. Okay, so this doesn't. You can see it's twisted.
It's not a cylinder. Definitely not a cylinder.
So I'm going to leave you to discover, to investigate this for yourselves, because there's a lot. It's a lot of fun to be had, and you could set it. You could do this with your class, because knowing the number of one of the words of permutations and combinations, permutations actually, knowing the number of possibilities here, counting them, thinking systematically. So you find all the possibilities, and then some of them are going to be the same. If you might start off doing it differently. Let's look at the pink one.
Toni, Vuyo says the first one. We're talking about the first one. The yellow one, Toni did actually reveal the amount of twists in that one. You might want to have a go at that one yourself. You can see them there, and you can replay this and maybe take a screenshot. Or and 2, if you're in AIMSEC, you can ask Toni for the PDF. So, and the thing is, there's 3 possibilities here in this image. How many more can you find? Are there? Because we're looking for all of the possibilities, and that is the activity we're wanting to find. Because we're looking at all the probabilities, we have to find all the possibilities to be able to talk about the probabilities. Am I saying that correctly, Toni? You are.
So the pink one, you can try the pink one too, and unders and overs. It's quite difficult to see what's happening, but can you see that this one hit, oops, this one hit this one, Because I'm looking at a mirror image of myself.
Totally,
I'm making a fool of myself.
No, you're not making a fool of yourself at all, but it is amusing.
So this is an under. Okay, as you go round, it's under.
And if any of you are thinking, oh my goodness, I'm not sure which is under and over, you're not the only one. I'm having the same experience. So I should be actually doing this myself. I should go through that.
I'm calling it under because what comes afterwards? Say this one, okay? It's underneath. I think for me, when I do it for myself, I'm going to think behind and in front. It's just me. Just each individual have their own way of this is
becoming
behind
comfortable with it.
That.
Yeah.
So this is what I'm calling.
So you're folding
under.
it behind or under.
And this is behind that one. It's under, and they're all under. Now, actually, when you, I use different coloured strips, and they have different numbers of twists, and it's a really nice challenge, and it's fun, and you can get your whole class doing it, and to work out systematically how many possibilities there are takes some mathematical thinking. And believe me, thinking mathematically, working systematically is far more important than learning a lot of facts which the computer knows and will remember and you might forget. Okay,
that is so true. This is something I never did learn to do. I'm learning now to do it, and I can get so stuck thinking, oh, I haven't worked out. I'm not in the habit of being systematic, and I'm learning the habit of being systematic. And when I work out how to log something or how to log all the possibilities, I did it the other day for something we did on Saturday. I was writing out, I wrote down all for the triangles, for the impossible triangles, and I just wrote them all out, and then I knew I could circle the ones that were possible and just ignore the ones that weren't. But I could really see it, and I wasn't guessing, and I was being systematic, and I really enjoyed it because I knew certainly exactly what would work and what wouldn't.
Now, what I mean is, here you've got 4 unders as a possibility, or you might have 3 unders, but the order in which they occur, under, over, or under, over, or the over in the second place, or the over at the beginning, they're actually a different sequence, aren't they? Or you can have 2 unders and 2 overs, and all those different arrangements of unders and overs, 6 of them.
Okay, and are they the same thing?
Well, what do you mean, Caroline? Are they the same in the sense of them ending up with either 0 twists or 2 twists or 4 twists or whatever number twists? Have they got the same number of twists? And, you know, when you say, are they the same mathematically, you've got to describe what you mean by the same.
Okay.
Now if you look at at those 3 loops there, you'll see that the red edge and the red edge meet in each case, okay, and the black edge and the black edge meet in each case. So there must be an even number of twists. That's a clue.
That's a clue, isn't it?
And we've seen that the orange one is actually a cylinder. What about the other 2? I'm leaving that for you to find out. But can you see the system in the lists there? They are what we call permutations or arrangements of the U's and the O's, the unders and the overs.
And can you create all of those 3 examples from the list that you've listed?
Yes, they're there,
you're answering it, Toni. But the point is, are those 3 images, did they, in some way, whether it's backwards or forwards, how would you use those to represent every single one of those possibilities?
I'm not sure what Caroline is saying. I don't understand. Okay. What I'm trying to say is that if you're being systematic, the U's and the O's, and there are four corners, and the four possibilities. There's two at each corner. So mathematically, there is 2 times 2 times 2 times 2, and that's 16 possibilities. And the 16 are listed there. And if you count the number of U's, there are either 4 U's, or 3 U's, or 2 U's, or 1 U, or no U's. And the different arrangements or permutations are listed there. So you can see all the possibilities. Now, you've got only 3 of them on the right-hand side, but they are different, those ones. But there are obviously 16 possibilities, and it will turn out that some of them will give you a cylinder, and some of them will give you 2 twists, and some of them will give you 4 twists. And in that sense, they're the same. And you've also got a sort of cyclic pattern, because you can start anywhere, really. So there's a lot to think about and a lot to discover in that. If you have your whole class doing it in groups, let's say they work in pairs, and then together they bring together their results, and this provides a check, because it's easy to make a mistake, and we learn from our mistakes. But if somebody's got it wrong, probably more people have got it right than wrong. And anyway, you can all talk about it and decide between you what is the right answer.
So this isn't just an enrichment activity. This is part of the training, of the discipline of learning to work systematically and finding all the possibilities and proving that you have found all the possibilities. This is actually this is a great exercise to do with your learners, to train your learners to be effective mathematicians in terms of writing down all the possibilities.
But more than that, if you want your children to pass their exams, almost every country... That's
always a positive thing.
Yes. Almost every country has teachers about probability, and the children have to do this sort of thing. They have to find out how many possibilities there are in order to be able to work out probabilities.
So we can use a subject that they don't have to learn, that's a very interesting subject, in order to do an exercise that will be helpful for them to
this isn't
do
topology.
Things they do have to know. Oh,
this isn't topology. This is algebra, actually.
But the twist,
or probability.
I thought the twists were about topology.
Yes, yes. And then you can talk about, you can spend 10 minutes or half an hour discussing how topology is important and useful, and mathematical models, and everywhere in the world people are hearing about COVID and hearing about the data. The mathematicians are making models, and they're trying to model the epidemic and see what's happening. Of course, the models are not the same, but in some ways they behave like the real situation. And the closer they are, the mathematics is, to the real situation, the better the predictions. And it's not a perfect world. I mean, we all know that quite often the weather forecasts are wrong. And okay, it's because it's very complicated, but it's the best, we do the best we can. And the model is mimicking, if you like, it's trying to be as close to the reality as possible. And we can do things with our computers which can think fast and crunch the data very fast. We can do amazing things with the computers if we understand what we're doing.
Yeah.
So briefly, the mathematician is using many dimensional spaces and working in that sense, they're working in topology. And the pure mathematician,
because they've got different parameters
that change. Yes, yes. And they may sometimes use geometry, but often they don't need the geometry. They're actually studying different features of these many-dimensional systems. And they're making models of physical situations in the real world and solving problems and helping to make life better for people in the world. And if the model isn't a perfect model, they can work on it and make it better. And sometimes mathematics predicts some physics that it's just theory, it's just pure mathematics, well, maybe maths mixed with some knowledge of physics or some other science, but it predicts something. And then later on in the real world, we actually find it really is true, and the maths knew it already, but we haven't actually proved it in life. So that's what happened with this particle, what was called the Higgs boson now. Higgs discovered this particle by doing mathematics back in 1964, and it wasn't until 2012 that at CERN in Switzerland, they actually discovered one of these particles, and then he got a Nobel Prize for work he'd done so many years before.
And he just used mathematics to predict that this particle existed. And
That's
then we were able to prove it using the particle accelerator.
There we go.
And pretty exciting things. And it was a mathematician that predicted it.
We run over our time.
Yeah, that's okay. We have a little bit of wiggle room. Okay. Thank you very much, Toni. Thank you, everybody. Oh, we've got a goodbye. We can't see the goodbye. We'll just say the goodbye ourselves. Goodbye. Thank you, everybody. See you next week.
Bye.
There will be a Happy Maths Hour at 5 o'clock London time next week, as there is every week. Thank you very much.
Bye-bye.
Bye-bye.